Welcome to our new electrical engineering course. Now in this course we'll be exploring the basics of electrical engineering that will be required for us to do mechanical engineering, which is our end goal at the end of this course. So we will be beginning with chapter 1, which covers 3 videos. This is the first part of our 3 video series for chapter 1. Now part 1 includes matter and atoms. So we'll be exploring that, and I hope you can enjoy. Now you always hear engineers say copper is a very good conductor. Well, that's what almost every lecturer says. Well, we'll be exploring what makes copper a good conductor in this video. I'll be going deep into the foundations, the building principles of copper, and what makes it such a good conductor. In doing so, I'll be making it clear of how electricity is made and how electrons and atoms work together. Now we know matter is made into 3 phases, which is solid, liquid, and gaseous. But our friend here, which is copper, is mainly made out of solid. Now, if you would zoom inside this copper wire, what you would find? You'd find a nucleus, and in that nucleus, you'll find a proton and a neutron surrounded by electron clouds. Now, I'm not sure how many they are, but there's a cloud. In this cloud, there are electrons rotating or revolving around this nucleus. But how do you know actually how these electrons exist? How do you know and how we test that? Well, imagine there's a metal solid sheet here. We can take it as infinitely thin. So it's thin like this. It's very, very thin. I will not consider its thickness, this example. And let's say we take an ultraviolet light and we'll shine some UV light rays onto it. Now, this metal is cold. Now, what will happen? You should look very closely here, is that the particles will be spontaneously ejected from this metal plate. What particles, you say? Now, these particles can be tested under different conditions, and it is believed that these particles also form part of the subatomic particles. In fact, they are elemental particles that also form a constituent of matter. Now, these particles will be called electrons. That's how we know, or at least that's how we've tested it. And we are sure that they might exist. Well, you can also test it using a microscope, and you could find what I'm talking about. In fact, we use a modern theory called the modern electron theory. Now, what does it state? It states that an atom is composed of 3 fundamental particles, which I've said when I was beginning this lecture, which are neutrons, protons, and also electrons. Now, to help us remember correctly and what's it important to know is that let me draw up a table, and let's say this is a matter particle, and next to it we'll write a symbol. Next to that, it's nature. Next to that would be the mass in kilograms. So a neutron, how to label a neutron? We'd label it with an N, and its nature would be 0. And how heavy would it be? Well, it would be 1.675 times 10 to the power of negative 27 kilograms. And we'd also have a proton, which would be represented by P plus, and would be of positive nature, and it would have the same mass, just 10 to the power negative 27. Now our star player here, which is an electron, so by E to the negative, and it would be of negative nature, having less mass, which is 9.107 times 10 to the negative 31. Now, these are one of the most fundamental things you should know in this chapter. You should know this at least by head. Okay, so how is the structure of an atom formed? Like I drew it here. This was just a rough sketch. Well, all protons and neutrons are bound together into a compact nucleus, as I've drawn in here. You see, or let me try and draw it again to further make my example noticed. So this would be the nucleus, which contains a neutron and a proton. And you'd have your first shell here, the second shell, and comes our third shell. Well, there are rules within this shell, but I will explain it as I go along. Now, the nucleus may be thought of as a central sun about which electrons revolve in a particular fashion. Now, what will happen is that there will be electrons that are around this cloud. There will be an electron here, there, you know. Let me spontaneously put them here. They will form what is called an electron cloud. Now, these electrons will be revolving around this nucleus that is also formed by a neutron and a proton. You should know that by heart at least. Now, let me continue on. Electrons will be arranged into different orbits. Now, you can call this shells or orbits, the same thing, but there are rules to this. And these electrons are held up by a force of attraction that's coming from this nucleus. Let me try and make a sketch of that. This nucleus will try and pull these electrons towards it, as I would say it's analogous which what is happening to the planets. They are attracted to the sun. So this is also what would happen, that these electrons are being held by this nucleus, so they won't fly off so easily. But now, here's the problem. The electrons on the outside of this electron cloud are called, or the area or region outside this electron cloud, or the last shell within this electron cloud, would be called the valence cell. And the electrons inside this valence cell will be called valence electrons. Now, these valence electrons will have the weakest force of attraction, which means they are more susceptible to being captured by other atoms or flying off, or I could call them free electrons, given enough energy. Now, going back to what I've said about copper. Now, if you have more of the number of free electrons, the better is the metal for the conduction of current. For example, the copper that I made an example of earlier. Now, copper contains 8.5 times 10 to the power of 28 free electrons per square meter, per cubic meter rather. square meter is rather small, so per cubic meter, and hence copper would be a good conductor of electricity. Now there are rules to this. You can't just arrange them randomly like I did so earlier. There are rules, meaning each orbit consists of a fixed number of electrons. An orbit can contain a maximum of at least 2 to the power n squared electrons. Now what does this n mean? Where n is the shell. So for example, in the first shell, there would be 2 to the 1 squared, which is equal to 2 electrons. Then for the second shell, we have 2 to the power 2 squared, which would be 8 electrons. But now here's the funny part. On the last shell on our atom, which is the valence shell, its rules are not bound by this law here. What will happen is that the maximum number of electrons that are accepted by the valence shell is 8, irrespective of its number. So let me make a quick side note here. So NB with the exception of the valence shell, it can occupy a maximum 8 electrons, irrespective of its number. And now I'm gonna make example of 2 different atoms here. I'm gonna draw a hydrogen atom, and I'm gonna draw a silicon atom. And how would we place these? Well, a hydrogen atom contains 1 proton and 1 electron. It's the most simplest particle you could ever see there. So here's this nucleus, and here is this electron cloud, and there's 1 electron. Now for a silicon atom, we've got a different story. Let me draw my nucleus to be small so that all the rest can fit. Oh, before I draw the others, let me conclude this. It contains 14 electrons. Silicon atom contains 14 electrons. Okay, so in the first ring, how many electrons would we have? We'd have 1, we'd have 2 electrons. Second ring, there we go. How many electrons would we have? We'd have 8, we'd have 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now how many electrons are left? There's probably 4 electrons left, so only 4 can fit on this valence shell, meaning that these 4 are a bit susceptible to be taken by other atoms. And that's the end of the first part of this video. We'll go to the next part where we'll be discussing the relationships between these parameters of electricity.